All right, so this lesson is about quadratic transformations. And so last class we talked about how the quadratic parent function, the simplest quadratic function we can have, is the function f of x equals x squared. So I'm going to go ahead and graph him so we can see what he looks like. He's a parabola with a vertex at 0, 0. And so transformations just refer to how the function is different from the parent function. So you can think of the parent function as the original function. And so I like to use this gear and change it to a dotted line, because he's the starting function. Every other parabola is just a transformation of this guy. And so we can do different things. We can reflect the function. We can move the function left, right, up, and down. We can stretch. We can shrink. And so I'm going to fill in these by just doing some explorations. If my new function, we'll call it g of x, is the x squared with a 2 multiplied, so 2x squared, or let's do something more dramatic. Let's do a 3. Notice the blue function is narrower, and so the bigger I make that scale factor, the narrower the function gets. And so the starting function, the red function, is a little bit, it's normal, and then the blue function is really narrow. And so the more we increase the scale factor, the narrower it gets. It's because we're vertically stretching it. If you think of stretching a rubber band, the more you stretch it vertically up and down, the narrower it looks. And so anytime you have a scale factor, we'll call that a scale factor, just means you're multiplying a scale factor. If that number is bigger than 1, so for example 2, 3, or even like 3 halves, as long as it's bigger than 1, we call it a vertical stretch. And it makes the function narrower because it's taller. The taller it is, the more narrow it looks. And so if I start using really small numbers, like say 1/2, or even 1/3, or 1/10, we can see the function gets really, really wide. And so that's because we're vertically compressing it. We're making it shorter so it looks wider. So vertical compression. These notes call it a vertical shrink. Shrink is another name for compress. And so it becomes wider because it's shorter. Okay, and then if we start putting negatives on these scale factors, whether it's a fraction, whether it's a whole number, it becomes upside down. And so it doesn't matter what the scale factor is. I don't even have to have a scale factor. If I have a negative there, it's going to reflect it. Reflect across the x-axis, because if you reflect it across the y-axis, you're not going to see a change. In fact, if I put parentheses around this x, and put the negative inside, it's now, we don't see the reflection anymore. It looks like the parent function. If I delete it and put it outside the parentheses, now I see it. And so a negative inside the parentheses is actually called a reflection across the y-axis, which is our axis of symmetry, which is why we don't see it. And so we can also put the scale factor inside parentheses, inside the square. And so that's another place to put the scale factor. Anytime it's in front, it's being multiplied, it's called a scale factor. And if it's negative, it's a reflection across the y. Then you're not going to see a change. And so when I say a is less than 0, that just means negative. And then if a is between 0 and 1, that just means it's a fraction or decimal smaller than 1. It could be 1/2, it could be 1/10, it could be 2/3, as long as it's smaller than 1. Okay, and so if I put the fraction scale factor inside, it's still wider, but this time we call it a horizontal stretch. And so a vertical compression is going to end up being the same thing as a horizontal stretch. Both result in a wider graph. It depends where you put the scale factor, you just change what you're calling it. Both are wider. And so the smaller the scale factor, the wider the function, regardless of where it is. And so a large value inside the parentheses, like 10, is going to make it really narrow. And so we call a narrower graph inside, or a narrower graph resulting from a scale factor inside, a horizontal compression. These are the hardest transformations, okay? And so we'll look at some examples. The easier transformations are left, right, up, and down. So that's what we'll look at next. And so looking at if I start adding a number inside or outside. So here I'm adding a number, here I'm subtracting a number. We're going to see what happens. And so here, if I do x plus 3, it actually moves it left. Okay, and so let's use green. Left C units. Whereas if I change it to a minus, it's going to move it right. Seems kind of backwards. It's backwards when it's inside. So this is going to move it right C, whatever that C is. In this case, I'm using 3. And then here, for this number outside the parentheses, if it's greater than 0, that means you're adding a number. If it's less than 0, that means you're subtracting a number. And so let's try to add a number and subtract a number. So outside the parentheses, if I add 3, it moves up 3. And if I subtract 3, it moves down 3. Okay, and so we used to have to memorize what all these numbers did, and some of you will naturally just memorize what these numbers do, but with Desmos, you can always graph to see what's happening. And so here on number 1, I see a scale factor outside. So I have a 3, and then remember, x squared is just our parent function. So you're going to see x squared in all of these. That's just the parent. Gosh, I can't highlight the 2. Okay, and so that 3 is a scale factor outside the parentheses, and so that's going to be our vertical stretch. Okay, on number 3, the 5 is inside the parentheses, so we're not going to call it vertical, we're going to call it horizontal. And we know the bigger the number, the narrower it gets. And so that's our horizontal shrink. And then this negative outside is our reflection over the x-axis. And so when in doubt, you can graph these functions. And so if I don't know my transformations, I'm going to graph that. And I see that the green one is reflected. And as soon as I see that it's reflected, I delete the reflection so I can compare whether it's narrower or wider. And so I can tell it's narrower. And because that 5 is inside the parentheses, I'm going to call it a horizontal shrink rather than a vertical stretch. Okay. On this next one, the negative is inside the parentheses, so that's the reflection over the y-axis. And then the 1/2 inside, it's a smaller number, so I know it's going to be wider. The smaller the number, the wider. And because it's inside, we know it's horizontal, and so a wider is horizontal stretch. And then this +1 outside, that's the wrong color, moves up 1. Okay, and so when in doubt, we can graph this. Graph it when you're typing it. Make sure you're typing the parentheses. Make sure you're typing it exactly how it looks. Okay, so there it's wider, and I can see that the new vertex is 0, 1 opposed to 0, 0. So that's how I know I moved up. And so once you note that it's been moved up, you can delete that +1 to compare how wide it is. It's a lot wider, so it's a horizontal stretch. And then there's a negative there, so I know it's reflected, but because it's inside, it's reflected across the y, which is why we don't see it. Okay, on number 2, I see a +5. And so I know it's moving up. When in doubt, you can graph x² plus 5 and see that it's been moved up 5. Once you've noticed it's moved up 5, you can delete the up 5 to compare and see it's not wider, it's not narrower, so that's the only thing that's happened. Okay, this next one, the -4 out here is going to move it down 4. This last one, the -5, is going to move it down 5. Okay, and then we also have a scale factor. And since there's no parentheses, that's going to be our vertical stretch. Okay, and so if I graph that, I need the 2 in front. I need a -4 outside. And so there's the down 4. And once I note that, I'm going to delete it. And then the 2, I notice it's narrower. And because the 2 is not inside parentheses, narrower is going to be a result of a vertical stretch. If I stretch a rubber band, the more I stretch it, the more narrower it gets. Okay, and so these next examples where they're using the function notation, you can do the exact same thing. And so a 2 outside the parentheses is going to be our vertical stretch. This 1/2 is going to be a vertical compression or vertical shrink. Shrink and compression are the same thing. This 7/4 is going to be a vertical stretch because it's bigger than 1. Here we don't have any kind of vertical or scale factor outside. Here we have a scale factor outside, so that's our vertical stretch since it's bigger than 1. And here we don't have a scale factor outside. Let's look for some scale factors inside. And so here we've got a scale factor inside. It's smaller than 1, and so we know it's wider. And so wider would be horizontal stretch, using the word horizontal instead of vertical because it's inside. Okay, and then let's look at for those negatives. Here the negative's outside, so it's reflected over the x-axis. Negative outside, reflect over the x-axis. Negative outside, reflect over the x-axis. Let's look for negatives inside. Here we've got a negative inside, so that's reflected over the y-axis as well. And then let's look for left, right, up, and down. I was using green for that. And so here we've got a right 10, because it's minus. Remember, you can graph these, and you can even use the F notation. So 7/4 F of x minus 10. Make sure you're typing it just like it looks. And so I can see that it's moved right 10 units. Okay, and so if I delete the right 10, I can compare that and see that the black is narrower. So because it's narrower, that means I'm stretching that rubber band. I'm vertically stretching that rubber band to make it narrower. Okay, it's important to note that, like, when I typed this minus this F notation, you have to tell Desmos what f of x means. If I were to delete the parent function, Desmos won't graph that. It has no idea what you're trying to graph. But as soon as you define what f of x is, you have to type this part first. Okay, and so let's see. Here we've got a -3, so that's going to move us right 3. When in doubt, you can type that in. -3 moves me right 3. And then this -8 is going to move us right 8. All of these were right. Okay, and then for the up and down, if I put a -1 outside, it's going to move it down. And you can check -1 and get rid of that -3. Moves it down. This one hasn't been moved up or down. This one's down 12. This one's up 2. I can put the +2 so you can see that. Up 2. And then this one would be up 3. Okay, and so you can either do these from memory or you can graph them each time and just look at what happened to the graph. The hardest thing is remembering the vertical stretch versus horizontal. And so if you want to put a summary out here, so if you have the function like 3x squared, this function is going to be narrower. And so is this function with the parentheses. In this case, you're calling it a vertical stretch because the 3 is outside. In this case, you're calling it a horizontal compression. Just because of where you're putting the scale factor. Okay, but both of them result in a narrower graph. The parabola is going to be skinnier than the parent function. Okay, and then over here, if I use a fraction, so if I had 1/3 x squared, and then over here I had the same thing, but the 1/3 inside the parentheses, they're both going to be wider. But in this case, we're going to call it a vertical compression And in this case, we're going to call it a horizontal stretch. Because the 1/3 scale factor is inside the parentheses, and here there isn't parentheses, so it's technically outside.